Okay, thank you very much, Aitse, for the kind invitation to give a talk here. So the topic is, as Aitse said, it's applications of the Stone-Weierstrass theorem in the Calderon problem. And this is based on a recent work with Mikko Salo, who is also from Finland. And there's a link to the archive version of the paper below. So there seems to be a slight lag in the connection, so I'll try to take that into account. So let's start. There's a little bit lag now. You should see my first slide now. So I'm not completely aware of your background. What inverse problems have you been studying? So let me start very easily, and let's first define what are inverse problems in the first place. To define what are inverse problems, let's first define what is a forward problem. So in science and engineering, one builds theories and models that are used to make predictions of outcomes of experiments. A model can be a partial differential equation, which I will abbreviate by PDE, such as Laplacian u plus QU is 0. So this equation is called the Schrödinger equation. Here, Laplacian of u, is delta u, is the normal Laplacian of the function, which takes the sum of the second derivatives of the function. Q is a function on this domain omega in Rn. And this equation can, for example, be used to model an electric potential U in a material whose conductivity is described by this function Q. So now, assuming that this Q is known, one can ask what is the electric potential U inside of this domain omega if U is fixed to a potential F on the boundary dou omega. So we give a boundary value for this equation, Laplace u plus QU is 0. So now solving this equation with this given boundary value F, this is called a forward problem. By the way, if there's some like a issue with my voice, please let me know.
You are good.
Okay, great. So then an inverse problem. So in the above forward problem, the function Q was known and the solution function u was unknown inside of this domain omega. An inverse problem for the above model is the following. This is an example. So now assume now that the function q is not known inside the omega. In this equation, Laplace u plus q is 0. An inverse problem asks if we can find out q by measuring properties of solutions to this equation on the boundary dou omega. Note that we don't know what is the solution u inside omega, because in that case, this problem would be trivial, and you could find q just by dividing this equation by u. But we know some properties of u on the boundary of this solution u. Applications of this above inverse problem arise, for example, in medical imaging, such as correct treatment of brain strokes, geoprospection, such as detection of oil and water wells, and in non-destructive testing of materials. A little bit more exotic applications are in invisibility cloak. In general, in inverse problems, measurements made on the exterior of a body are used to deduce properties of the inaccessible interior. So now we know what is an inverse problem. So then I said that we know something about the solutions u on the boundary. And how do we model these properties of u on the boundary? So measurements on the boundary, these are mathematically encoded by the so-called Dirichlet-Neumann map. And it is defined as follows. So you take a function on the boundary of omega, this small f. Then with this boundary value, this boundary value function f, you solve the equation 1. So you solve this Laplace u plus q is 0 with this boundary value f. Then the Dirichlet-Neumann map, it maps this function f on the boundary to another function on the boundary, which is given as the normal derivative of the solution to equation 1 on the boundary. So take a function on the boundary, solve the equation with that boundary value, and compute its normal derivative on the boundary. That is the Dirichlet-Neumann map. Here n is the normal vector field to boundary of omega. Physically, the Dirichlet-Neumann map, which I will abbreviate by DN. It corresponds to electric flux, which goes through the boundary of omega, which is generated by the potential F on the boundary. So if F is like a positive on the one side of omega and negative on the other side, there will be a current, and this Dirichlet-Neumann map measures how much this current goes through the boundary. So this is the Dirichlet-Neumann map. Okay, so now we know what is the Dirichlet-Neumann map, and we are ready to formulate the one of the topics of today, which is the Calderon problem. So using the Dirichlet-Neumann map, we can formulate the Calderon problem, which asks, determine the function q inside omega from the Dirichlet-Neumann map, which is denoted by lambda, of the equation Laplace u plus qu is 0. So your task is to determine this function q inside omega. Let's make some observations about this problem. So let's start very easily. Does this make any sense, this problem? And so note that now that this DN map lambda, it depends on this unknown function q. And the reason for that is that the DN map, which computes the normal derivative of the solution of the boundary, the solution depends on q implicitly through this equation Laplace u plus q is 0. So at least there is some point in this problem. So lambda really depends on this function q. Another observation is that the Calderon problem is so-called nonlinear inverse problem. And the reason why it's called nonlinear is because the DN map depends non-linearly on this function q. So the dependence in this equation is implicit, and it's also non-linear. Let's then try to make a little bit more sense how well posed this problem is. And let's do some variable counting now. So now the unknown potential q, it depends on n variables. So omega, recall that it's a domain in Rn. You can see the Dirichlet-Neumann map. It's a mapping from functions on the boundary to functions on the boundary. So you can write this operator using its kernel, namely its Schwarz kernel. And you see that the Schwarz kernel is a function on the boundary of omega times boundary of omega. So now the boundary of omega has dimension n-1. So the Schwarz kernel has dimension, or it has variables of the amount of 2 times n-1. So given this, we see that this Calderon problem is formally well posed in dimension 2, because then this n is the same as 2 times n-1. It is overdetermined in dimension n is more than 2, and it's underdetermined and not solvable, in fact, in dimension 1. So in dimension 1, you cannot get much information about this q from the DN map. So in a sense, if you look at this, so well posed is like the optimal case where you can sort of like expect to solve this problem, and overdetermined should be easier. In practice, it doesn't seem to be that case, but philosophically speaking, it's like that. Okay, slight lag now. So the Calderon problem in the last slide was maybe the simplest of the Calderon problems. So there's many different types of inverse problems for PDEs, which are called the Calderon problem. Probably the most famous of these inverse problems, sometimes called the Holy Grail, is the anisotropic Calderon problem, and it is the following question. So it asks if you can determine a Riemannian manifold, Mg, so M is a manifold, G is a metric. I will explain in a while what are those. And this manifold has a boundary, dou M. And you need to determine this Riemannian manifold from the corresponding DN map, Dirichlet-Neumann map of this equation Laplace Gu. This kind of mess, I will explain in a second, is 0. So this is the Laplace equation of a Riemannian manifold. This delta G is called the Laplace-Beltrami operator. And here in this problem, this M can be topologically complicated. But never mind about the manifold. Let's just think about that you have a, let's say, a ball in Rn, and then you have this equation where this G is a matrix valued function. And the task is to determine this matrix valued function G from the Dn map of this equation. So the Dn map is again defined as earlier. Give a boundary value for this equation, solve the equation, compute the normal derivative of the solution. So this problem is about 40 years old, and it's generally very much open. So this is slightly my own opinion, but I think this is well agreed in the community that it's quite open still. Solution to the above anisotropic Calderon problem, and this is sort of the reason why it's called the Holy Grail, is that it would lead to solutions to many other inverse problems as well. So if you can solve this anisotropic Calderon problem, you can solve a lot of other related problems as well. This anisotropic Calderon problem, it can only be solved up to a coordinate transformation or diffeomorphism, if you will. So studying the inverse problem of manifolds is natural. So when you study this inverse problem of manifolds, you get to then use all the tools of Riemannian geometry and geometry in general to study the problem. So it's a practical matter to study on manifolds. Okay, so let us then recall results on the Calderon problem. So for this simplest of the equations, which was this Laplace u plus q is 0 on the domain omega in Rn, identification of this potential q from the Dn map, the normal map, was done by Sylvester and Ullmann in 1987, and independent by Novikov almost the same year. In the dimensions n is at least 3. A little bit interestingly, the case n is 2, the case where the problem was formally well posed, it's like not overdetermined. It was only solved by Buchheim in 2008. So there was a very long gap between these results. Then you can study a related Calderon problem for this so-called conductivity equation, which is written as here. So you have a divergence of sigma times gradient of u. So sigma here is a conductivity function, and this is called the conductivity equation. And you can again define the Dn map as previously. Solve the equation and compute its normal derivative. As a matter of fact, if you study Calderon problem for this equation, in the case that this sigma is smooth enough, it actually reduces to the Calderon problem of this Laplace u plus q is 0. However, in the case when sigma is not smooth enough, in dimensions n is at least 3, when the conductivity function sigma is only Lipschitz, identification of sigma from the Dn map was done by Haberman and Tatarov 2013. In dimensions 2, there's very good result, and in that case, the conductivity can be even till infinity. And the identification of sigma in that case from the Dn map was done by Astala and Päivärinta. These are, by the way, Finnish guys. I'm from Finland as well. Right. Then there's so-called partial data Calderon problem. And in that case, it is assumed that your boundary value f is supported, and you only measure the normal derivative of the solution on a subset gamma of this boundary dou omega. So in this case, called the partial data problem, in dimension 2, this problem is solved by Imanogilov, Ullmann, and Yamamoto in 2010. But in the dimensions n is 3 and higher, there's only a partial result by Genix, Sjöstrand, and Ullmann. In my opinion, this result is still quite far away from solving the partial data problem, even in Rn, completely. So how about the anisotropic case? So from now on, let me call all Calderon type problems where you have matrix valued coefficients anisotropic Calderon problems. So in this case, for the equation Laplace G plus QU is 0 on a Riemannian surface, so that means a Riemannian manifold of dimension 2, identification of this metric G in the case when this potential is identically 0 was done by Lasses and Ullmann 2001. Identification of this function Q when G is known was done by Guillermo and Zhou 2011. But the case when both G and Q are unknown, this was actually done only this year by Karstea, Meehan, and Zhou. How about the dimensions n is at least 3, so dimensions 3 and higher? So in that case, not much is known. Sort of the fundamental result is that when this Riemannian manifold is analytic and this potential is Q is identically 0, identification of this metric Riemann metric G was done by Lasses and Ullmann 2001. But note that now the assumption is that the metric is analytic, meaning that the Taylor series converge. Then the results on so-called cylindrical manifolds, which I will later discuss during this talk. In that case, the identification of the potential Q, assuming that the metric G is known, under additional assumptions was done by Dos Santos Ferreira, Koenig, and Ullmann, and Dos Santos Ferreira, Kurre, Lasses, and Salo in years 2009 and 2016. And then I also mentioned this nonlinear counterpart of this Calderon problem on cylindrical manifolds. I will mention a result about that here because I will discuss that later on today as well. So as it happens, for nonlinear equations, Laplace GU plus Q u to power m, where m is at least 2, there are actually better results. So this equation is nonlinear because the power of m is at least 2. So this is a nonlinear equation. Yes, so in this case, there are better results for the detection of Q from the corresponding DMAP. This was done by Hesma-Hammari and Oksanen, and at the same time by Lassas, me, Lin, and Salo. I will discuss this problem later today because we can solve that by using the stone wire stress. But let's go to that in the end. Okay, so that was the Calderon problem and what is known, the best results in my opinion. Okay, so let's go to the stone Weierstrass then next. So why the stone Weierstrass theorem can be useful in the Calderon problem. So for this, let's first discuss the so-called linearized Calderon problem. So the linearized Calderon problem for this equation Laplace u plus QU is 0 is the following. Assume that the function f integrates to 0 against products of any two solutions to the Laplace equation. So Laplace u1 is Laplace u2 is 0. And the task is to show that f is identically 0 in this case. So you assume this condition 2 for all u1 and u2 that are harmonic in the sense that they solve the Laplace equation. And your task is to show that f is 0. So this problem was originally solved by Calderon himself. And he used what are nowadays called Calderon's exponential solutions. And the solution is pretty simple. So Calderon's exponential solutions are given here. So u1 is e to power xi1 dot x and u2 is e to power xi2 dot x. Xi1 and xi2 are complex vectors. So they are of the form k plus I eta and xi2 is minus k plus I eta, where k and eta are vectors in Rn. It is assumed that k is orthogonal to eta and that k and eta have the same length. So with these choices for k and eta, we have that xi1 dot xi1 is 0. Recall that these are complex vectors. And the same for xi2. So this implies that these solutions, these functions u1 and u2, they are harmonic. So the Laplace equation. Also, note that we have k and minus k here. You see that the product of u1 and u2 is e to power 2 I eta dot x. So when you plug in this u1, u2 to equation 2, you actually have the Fourier transformation of f at Fourier frequency 2 eta. But now eta here was just arbitrary vector in Rn. So you can invert the equation f hat 2 eta is 0 to get that actually f is 0 by inverting the Fourier transform S. So this is how you solve the linearized Gardner problem in the most simple case. Okay, still nothing about this Stone-Weierstrass theorem. But before I go there, let's recall the theorem itself. So the standard Stone-Weierstrass theorem says that polynomials of the unit interval are dense in the continuous functions on that interval. A well-known generalization is the so-called complex Stone-Weierstrass theorem. And it goes as follows. So let X be a compact space and Cx the algebra of continuous complex valued functions over X. Let then A be a subalgebra of this Cx. Then the theorem says that A is dense in Cx, which is equipped with the supremum norm, if the following conditions hold. For all X and Y, X is not Y, there must be U in A such that U at X takes the different value than U at Y. In this case, it's called that A separates points. The constant function 1 must be in A. It's called that A is unital. And finally, if U is in A, it must be that the complex conjugate of U is in A as well. And in this case, A is called self-adjoint. I note here that I will use that if A is dense in Cx, it will be dense in L2 of X as well. When I apply this theorem in the inverse problem. So that was the Stone-Weierstrass theorem. Right, so let's now go back to the Gardner's exponential solutions and the linearized problem. So now we want to apply the Stone-Weierstrass. And for that, we set this capital X to be the closure of omega, the domain in Rn. And we set S to be the following set of functions. So S is the set of functions which are products of e to the power xi1 dot x, e to the power xi2 dot x, where xi1 dot xi1 is 0 and similarly for xi2. And now we will show that S is complete in the continuous functions over omega by using the Stone-Weierstrass theorem. And then it goes as follows. So first of all, we choose, or we let eta be arbitrary vector in Rn, and we choose this xi1 and xi2 as we had in the couple of slides before in this Gardner's exponential solutions. So xi1 is k plus I eta, xi2 is minus chi plus I eta, k is orthogonal to eta, and k and eta have the same length. So now it follows that the span of S, it contains the span of e to the power 2I eta dot x. So this e to the power 2I eta dot x was this e to the power xi1 dot x, e to the power xi2 dot x, when you have chosen xi1 and xi2 as here. So now we see that this A is an algebra, because if you take a product of two functions of this type, you get a function of the same type. It contains 1, you take eta to be 0, it's closed under complex conjugation as well, it just flips the sign of eta. Finally, this A also separates points. So if X and Y are in this domain omega, now we choose eta to be X minus Y. So in this case, e to the power 2I eta dot x is e to the power 2I eta dot y, if and only if e to the power 2I x minus y dot x minus y is 1, and that is equivalent to X to be Y. So if X is not Y, it will be that this e to the power 2I eta dot x is not the same as e to the power 2I eta dot y, which means that this A separates points. So recall that there was basically 4 conditions for the Stone-Weierstrass. First of all, this A needs to be an algebra, check. It contains 1, check. It's closed under complex conjugation, check. And A separates points. So we can apply the Stone-Weierstrass theorem to see that A is dense in the continuous functions over omega. This means that S is complete in the continuous functions on omega. Maybe at this point, I want to recall you that a complete set just means that its span is dense. Here. Okay, so let's get finally back to this linearized Gardner problem. And there the assumption was that the integral of a function f against product of any two solutions is 0. So now if we take u1 and u2 to be as here this e to the power xi 1.x, and similarly for u2, we see that f is orthogonal to this s in L2. But now since s is complete, we have that f must be identically 0. So we have now solved the linearized Gardner problem by using the Stone-Weierstrass theorem. So this is of course very simple application, but it's the first example. So the rest of the talk is about giving more examples of the use of the Stone-Weierstrass theorem in inverse problems, and I will consider 3 examples. The first one is the density of products of harmonic homogeneous polynomials in Rn. The second is linearized Gardner problem Kähler manifolds, and the final one is a Gardner problem for a nonlinear equation of cylindrical manifolds. I will just focus on the main ideas and how the Stone-Weierstrass theorem appears in these problems. If you are not familiar with manifolds, that should not be a problem, as the manifold sort of like only appears in the special form of solutions we have for the equations we are considering. So let's start with 1. So density of products of harmonic homogeneous polynomials. So this is a term we proved with Salo this year. So let omega be a bounded open set. Then the following sets are complete in C omega. So S2 are products of U1 and U2, which are of the form absolute value psi minus psi a to the power 2 minus n, where these points psi 1 and psi 2 are outside of this omega. And then this S3, which are of the form U1 and U2, where U1 and U2 are harmonic homogeneous polynomials in Rn. Actually, that S2 is complete, it's well known, and that goes back to Ries, and we only gave a new proof using the Stone-Weierstrass theorem with Salo. But the case S3, I think that is new, and let's then just consider that one here. So let's prove the claim for this S3. So we claim that harmonic polynomials, products of harmonic polynomials are a complete set in C omega. And we split that into 2 cases. So the cases when the Rn, the dimension of Rn is n, and n is even. So that is the first case, and then we consider the odd case after that. So in this even case, we write points of Rn as like x1, y1, x2, y2, and so on, xm, ym. And we also write j is xj plus iyj, and z is this m-length complex valued vector. So now with this notation, if we write u1 to be z to power alpha and u2 z bar to power beta, where a and beta are multi-indices, then these are harmonic homogeneous polynomials. So the span of S3, it contains the span of this z alpha, z bar to power beta, or any alpha and beta, like multi-indices. So we see that this A now is a unital subalgebra, take alpha and beta to be 0. It's closed under complex conjugation, trivially. And it also separates points. To say that you need to leave it work, but it's true. So it follows that this A is dense in the continuous functions on omega. And it means that S is, the span of S is also dense, which means that S is complete by Stone-Weierstrass theorem. So this completes the dimension is even case. How about the odd case? The dimension is odd. So in this case, I will consider a little bit simpler problem. I will only prove completeness in L2 instead of in this stronger realm of continuous functions. So this is just for simplicity. To go from L2 to C to a supremum norm, you need some functional analysis, but I don't want to go there. To prove this, we thus assume that f integrates to 0 against products of any harmonic homogeneous polynomials. And the task is to show that f is 0. So if we can show that, it follows that S is complete in L2. To prove this, we write the points of R2n plus 1 as x prime t, where x prime is a vector in R2n, and t is a real number. So now if we choose this uj's to be independent of t, and that they are harmonic polynomials, obviously, then we get this following condition, that the integral of over R2m, and then integral from minus infinity to infinity of this f x prime t against this u1 x prime u2 x prime is 0. But now if this u1 and u2, they were harmonic polynomials, as in the dimension even case, we actually can erase this first integral sign here, which means that we have that the integral of f in direction t, and this x prime is now fixed, is 0 for any x prime in this R2m. So you can think about, if you split the space into this R2m and t, you have that the integral of f against all vertical lines is 0. Right, but note now that this additional direction, which corresponds to this variable t, is nothing special. You can just rotate coordinates and repeat this argument in all other directions as well. So it means that the integrals of f over all lines in R2m plus 1 must be 0. So then there's a well-known result. It's called the injectivity of an X-ray transformation. It says that f must be 0. So this injectivity of X-ray transformation says that if a function integrates to 0 over all lines, the function is 0 itself. So now we have proven that f is identically 0, which was the claim. So we have now proven the completeness in L2, and as I said, going to the subliminal takes a little bit functional analysis, but let's not go there. So this is now proven. So that was the first example of the Stone-Weierstrass theorem in inverse problems. So let's go then to the next topic, which is the Calderon problem on Kähler manifolds. And again, what are Kähler manifolds? If you don't know what are manifolds, don't worry. So you can think about that Kähler manifolds are higher dimensional generalizations of Riemannian surfaces, in the sense that they have well-defined holomorphic functions. And probably many of you know what Riemannian surface can look like, a donut or sphere or something like many handles, two-dimensional surfaces. So this linearized Calderon problem on Kähler manifolds was solved by Guillermo, Salo, and Zhou, but they had some additional conditions. So now the nice thing about this Stone-Weierstrass theorem is that we can remove all but one of these additional conditions, and we proved the following theorem with Salo this year. So now we assume that MG is a compact holomorphically separable Kähler manifold with smooth boundary. And now we assume the condition of the linearized Calderon problem. If you recall, it was that assume that f integrates to 0 against products of any two solutions, and the claim was that f must be 0. And we proved that. So assume that f integrates to 0 against any product of two solutions, then f is 0. So this is what we proved. So Kähler manifolds were high-dimensional generalizations of Riemannian surfaces, but what is this holomorphically separable condition here? Holomorphically separable means that for any x and y in this manifold M, there's a holomorphic function u in M such that this u takes different values at points x and y. And let's prove this, and the proof is almost trivial now using this Stone-Weierstrass theorem, so it's pretty nice. To prove the above theorem, we set this A now to be the following set. So it's a sum of H1A1 plus H2A2 until H and AN, where now Hj is holomorphic and Aj is anti-holomorphic functions. So if you think about just in complex plane, this is some kind of, this has an expansion in the powers of z, and this Aj has an expansion in the powers of z bar. This is subalgebra of the continuous functions. Why? The reason is that products of holomorphic functions are holomorphic, and products of anti-holomorphic functions are also anti-holomorphic. So this set A is an algebra. A is of course also unital because the function 1 is holomorphic. It is also closed under complex conjugation. Why? The reason is that the complex conjugate of a holomorphic function is anti-holomorphic and vice versa. And then there was this assumption in the theorem that M is holomorphically separable. And this means that by assumption, this subalgebra A, it separates points in M. So this was the assumption in the theorem. And now the starting point of the main assumption of the theorem was that the function f integrates to 0 against all products of harmonic functions. But note now that holomorphic functions are harmonic as well as anti-holomorphic functions. So it means that f integrates to 0 against all elements in A. But now we have already seen that the conditions of the Stone-Weierstrass theorem are satisfied, which means that A is dense in the continuous functions, and also because L2 norm is the L2 topology is weaker, A is also dense in L2. Then by this condition that f integrates to 0 against these products, we have that f is identically 0, and the theorem is proven. So the proof is almost trivial in this using the Stone-Weierstrass theorem. I finally note that this proof also gives a new proof for the linearized Calderon problem in Rn and on Riemannian surfaces as well. So the only thing you sort of need to check is that the holomorphic function separates the points in these cases in R2, namely on the complex plane. That is easy to check. It is also true on Riemannian surfaces, but that is a non-trivial fact. But it's true. So we can use the Stone-Weierstrass theorem in R2 and on Riemannian surfaces as well. Okay, so the last example of the use of the Stone-Weierstrass theorem is in Calderon problems on cylindrical manifolds. And let's start by defining what are these cylindrical manifolds. Right. So cylindrical manifolds, as the name says, they somehow look like cylinders. In mathematics literature, these manifolds are precisely called transversally anisotropic manifolds, and they look as here in the picture. So the transversally anisotropic manifold is a subset, this pink area, of a cylinder manifold. And why it's a cylinder manifold is because this cylinder is a product of a unit interval, or interval a little more generally, in R, and a manifold M0. The metric, the Riemannian metric, is of the sum form, so it's the Euclidean metric in the vertical direction, and some given metric on this given manifold M0. Here, this M0 G0 is called transversal manifold. There's a generalization of these transversally anisotropic manifolds, which are called conformally transversally anisotropic manifolds. They are abbreviated as CTA, and they're exactly as here in the picture, but we now allow a conformal scaling function in front of this metric G. So C here is just some positive function on this cylinder manifold M here. Okay, so let's keep this picture in mind. So we have some kind of cylinder and we have transversal manifold at the bottom. Okay, so what is the Calderon problem? In this case, well, it's as usual. So now it's anisotropic because we have a matrix valued coefficients here. And the problem is as follows. So the task is now to determine this potential Q from the DN map, which again is defined as previously. Take a boundary value for this equation, solve the equation, compute its normal derivative on the boundary. And the task is to determine the potential Q from this DN map. We now assume that this G is known. So we only want to recover this Q now. And as I previously said, this was solved under additional assumption that this M0, G0, that was called the transversal manifold, is simple manifold, which basically means that geodesics can only intersect once, or that so-called geodesic X-ray transformation is invertible on this transversal manifold. Geodesic X-ray transformation is sort of like a curved version of the normal X-ray transformation. And the people who solved these problems were like David dos Santos Ferreira, Kenix Salo and Ullman, dos Santos Ferreira, Kurlet, Lasses and Salo, 2009-2016. And these results are sort of the best results for the equation. Laplace G plus Q U is 0. For the nonlinear counterpart of this above Calderon problem, it happens that there are better results. And this was done by Fes Mohammadi and Oksanen. They solved on conformally transversally anisotropic manifolds this problem of determining Q from the corresponding DN map of this equation under the assumption that some kind of weighted geodesic X-ray transformation is invertible on this transversal manifold. In this little bit more simple case, when we have only transversally anisotropic manifold, so no conformal factor in front of the metric G here, we gave a full solution with Lasses, me, Lin and Salo, and actually these two papers, they were posted on the same day. We realized that we are working on the same problem. So they a little bit overlap these results, but they're not completely like the same. Okay. Again, let's then discuss the Stone-Weierstrass. What has it got to do with this kind of problem? So first of all, the proof of the general case, which we gave in our paper with Lasses, Lin and Salo, it's technically quite challenging. There are a lot of parameters, a lot of geometry involved. It happens that using Stone-Weierstrass theorem, we can not just only generalize the result, which we gave in this paper I mentioned, but we can also simplify the proof quite substantially. So with Salo this year, we proved the following theorem. I call it density of 4 solutions. So here, let Mg be a compact, conformally transversal anisotropic manifold with smooth boundary. Now, if a potential Q, the function Q satisfies that its integrals against products of M, not 2 as previously, products of M solutions to the Laplace equation is 0, then Q must be 0. So what does this condition 3 have got to do with the Calderon problem of this equation? Laplace G U plus Q U to the power M is 0. The connection is that if you differentiate solutions to this equation, Laplace G U plus Q U to the power M, where you now put the boundary value depend on a parameter epsilon M times. If you differentiate these solutions M times, and then if you integrate by parts, this kind of quantity where you have the derivative Neumann map, you will end up with this equation 3. It's not a very long computation. So if we know the DN map, we know the condition 3, which means to solve the Calderon problem for this Laplace G U plus Q U to the power M is 0, it is enough to prove this theorem above about the density of 4 solutions. And let's prove that now. So now we have a little bit, there are 2 slides, and they're a little bit technically a little bit more complicated. But let me walk you through those. So to prove the theorem, we use the fact that on CTA manifolds, you can now think that the manifold is just a cylinder, M0 times the interval, which is now equipped with the metric of the form conformal factor times the Euclidean metric in the vertical direction and G0 in the transversal direction, M0. So in these CTA manifolds, there are special solutions called complex geometric optics solutions, abbreviated as CGOs. So what do these CGOs look like? They look like as follows. So there are functions US. S is now a parameter, complex parameter of the form tau plus I lambda. Tau is large, And in fact, we will be taking tau to infinity. And lambda is a parameter which we want to manipulate in the end. So US is e to the power plus minus s x1, where x1 is now the direction in the vertical direction of the cylinder. And then we have another function bs. So in a sense, these functions are obtained by separating variables. It's not completely true, but you can think about that bs is just a function on this transversal maneuver. You remember the picture I had in the beginning. So m0 was the bottom of this cylinder. So you can think about that v is a function on the bottom of the cylinder. So now we choose this bs to be so-called Gaussian beam, which is adapted to a geodesic on this transversal manifold m0 g0. And below here is a picture of the situation. So let me explain. So here this curved path is a geodesic on the bottom of the cylinder, so on this transversal manifold. And this Gaussian beam, it has the two fundamental properties. First of all, when you travel along this geodesic, the function will oscillate. And the frequency of the oscillation is controlled by this parameter tau. If you walk away from the geodesic, then you will have Gaussian concentration. And this is due to the reason that this so-called phase function psi here looks like t plus I norm of y to the power 2. So note that you have I here, so it's I. So this e to the power I s psi, it has a factor of e to the power minus tau y squared. So it's a Gaussian concentration on this geodesic. So these are now complex geometric optics solutions, which is a product of this e to the power plus minus sx1 and then a Gaussian beam. So let's get then to the inverse problem, which was about solving that products of four solutions are dense. And we now choose these four solutions as follows. It's a little bit messy, but let me walk you through. So first of all, we choose two parameters, lambda 1 and lambda 2. And then, there's no correction terms here. And then u1 looks like e to the power tau plus I lambda 1 x1. Then the Gaussian beam corresponding to this frequency tau plus I lambda 1. Similarly for u2, e to the power minus tau x1. And then Gaussian beam with frequency tau. And similarly u3 and u4. Recall now that these Gaussian beams here were of the form I e to the power is, and then in the brackets tau plus I y squared. So if you now take a product of these four solutions, you will have the following. So u1, u2, u3, u4. It looks like you have this x1 directions first here. You note that you first see that this e to the power tau x1 and e to the power minus tau x1 terms, they exactly cancel. So you don't have this e to the power tau x1s anymore. And also, if you look at recall what was this Gaussian beams look like, you will see that this product of these four solutions looks like this. So it's like e to the power I lambda 1 x1 and something similar in, well, e to the power minus lambda 1 t, e to the power minus I lambda 2 x1, e to the power minus lambda 2 t. And then you have something which depends still on tau. So it's e to the power minus 4 tau y squared. So this t is this t is the parameter of the geodesic. So when you travel along the geodesic, there was oscillation, and this y are coordinates which are transversal to this geodesic y, to this geodesic gamma. So if you know what are Fermi coordinates, these coordinates t and y are exactly Fermi coordinates. Note the Gaussian concentration to the geodesic due to this last factor here. So when tau goes to infinity, this function wants to concentrate at y0. In fact, now if you plug in these solutions, the integral identity, which we start from, which was that integral of q against a product of four solutions is 0. Now if you normalize this integral by suitable power of tau to the power n minus 2 over 2, and take the limit tau goes to infinity, we will see that we'll obtain the following quantity, which is integral over the interval of the cylinder times the parameter interval of the geodesic of a function q tilde. I will explain what is q tilde in a second. Of q tilde evaluated at x1 and on the geodesic gamma on the transversal direction. And then we have these functions depending on lambda 1 and lambda 2 as weights. I now have the same integral here again. So this q tilde is a positive multiple of q. Recall that we want to show that q is 0. So if we show that q tilde is 0, we are okay. And this was the quantity we obtained in the last slide here. So now we differentiate this condition 4 any number of times in lambda 1 and lambda 2 at lambda 1 is lambda 2 is 0. This gives, see that this factor here in the exponent, it pops out to times a and b. So you get x1 plus it to the power a, x1 minus it to the power b, and the integral is against this q tilde at x1 gamma t. And a and b are now arbitrary integers here. So now, of course, you see that this is just z, complex number z, and this is complex number z bar. So we have here z to the power a, z bar to the power b, and then by just the complex Stone-Weierstrass theorem, the algebra generated by z and z bar is dense. So it follows that using the density of these products here, we see that q tilde at x1 gamma t must be 0 for all x1 and all t, where x1 is in this interval I and t is in this parameter interval of the geodesic 0 t. So this means that q tilde is 0 on I times the graph of the geodesic gamma. So this I times the graph of the geodesic gamma is a two-dimensional surface. And we have now proven that q tilde equivalent to q itself is 0 on this two-dimensional surface. So this is not what we actually wanted to prove. We wanted to prove that q is 0 on this full cylinder, not just on two-dimensional surfaces inside the cylinder. But this the fact that q is actually 0 inside the full cylinder can be obtained by varying the geodesic on this transversal manifold. And then we just repeat the argument for this variation of these geodesics. This shows that q is 0 on this full cylinder, and this proves the theorem. This basically ends my talk as well. So here's a summary of what I wanted to explain to you.